Time for us to do some problems involving sketching in polar curves, and we'll also do some tangents on polar curves. As always, as we start new topics, it's important to do practice. As we practice, we get better, and we want to get better. That's the goal. We don't start something to get worse. And so keep practicing as much as you can. Do these on your own. If you're following along with the video, make use of the pause button. See a problem? Try it out and see what you get. And then you can unpause and we can compare our answers. So, let's begin. Our first problem. Sketch the curve r equals 1 minus cosine theta and identify any symmetry. And also repeat this for the curve r equals 1 minus sine theta. Okay, cool. So, what are we after? Well, let's start with the 1 minus cosine theta, because after all, it did stay to start there. If we think about that, suppose we weren't in polar curves. So we were back in our old mindset. We said, oh, I can sketch this if I think of this here as not as in the plane where we have our r and theta, but let's think of our theta as our input and r as an output. Then 1 minus cosine theta, well, that's not so hard to draw. You can sort of build your way up to it, right? Because cosine theta would do what? Well, it would normally look like this. And negative cosine theta would flip it over. And then when we put a 1, it shifts it up. So the result is that here, it'll look something like this. So this is 2 pi. And over here, at the peak, it's at a height of 2. And halfway, by the way, is pi. Okay, now, this is not the polar curve. Or rather, we should say, this is not what the plot looks like in the plane. What we're seeing is, okay, how does r and theta relate? How do we take that information and produce a picture? Well, we think about what's going on. So, we'll have here our plane. So here's our plane now. And now what we do is we look at the following. We say, what are the interesting points? Well, for us, interesting points are when we're at 0 or when we're far away. Okay, well, then there are some definitely interesting points. So, namely, at 0, at pi, and at 2 pi. So we can see the following. At 0, we're going to be at distance 0, and similarly at pi. So that means that at this angle, at theta equals 0, which is the same, by the way, as theta equals 2 pi, because going 2 pi is a full circle around. We're going to start at 0. When we are over here at theta equals pi, well, we're going to be how far? Well, we have r equals 2, so that says we're going to go out a distance of 2. So there's that point there. Now, notice I didn't put negative 2, because here that 2 is indicating a distance, which is value for r. So this is not the x coordinate that's being represented, it's saying how far are you from the origin. And you can plot other points. It's not so hard, for instance, to see if you go at pi over 2 or 3 pi over 2, you're only halfway there. So you're at 1. So we're at 1 and at 1. But what are we really after? We're after the behavior. And so we say, look, our behavior says at 0, we start at the origin, and then we keep getting further and further and further away until we hit to pi. And then at that point, we sort of start turning around and coming back. So we start moving out until we hit 2. Okay. And then we start coming back until we come in. So that's a rough picture. Okay. Now, you might say, okay, is it good enough? And for our purposes, yeah, it is good enough. Now, one of the things that you can do to help you sort of think about what's happening is you can think of it in the following way. As we move here from left to right, what's happening down here is that we are rotating so that we start and then we start turning. So that there's this pivot here. And we're saying, how far out do we go? So again, scanning here from left to right is the same as saying what happens as we go through in a rotation around. Okay, so that's that's the idea. That's the sketch. Now, it says identify symmetry. So let's see if we think we see any symmetry. We can see if we pick it up and turn over that way. No, it doesn't look the same. But it looks like, modulo our ability to draw, well, that can be pretty big. It seems if we pick it up and put it back down, we do have symmetry. In other words, it seems to match. Now that's symmetry with respect to the y-axis. Now, how do we know if we're symmetric with respect to the y-axis? Well, we're going to be symmetric with respect to the y-axis. Sorry, not the y-axis, the x-axis. We're going to be symmetric with respect to the x-axis, pick it up, put it back down, if the function at negative theta is the same as the function at theta. Well, in our case, our function is 1 minus cosine. Now, if we plug in 1 minus cosine of negative theta, well, cosine is an even function. And so, since it's even, it's the same as 1 minus cosine theta. So, yes, it does have our symmetry that we're after. Good, good. All right, well, now we'll do the other curve. Okay, r equals 1 minus sine theta. So again, let's sort of think about, well, what is the curve r equals 1 minus sine theta look like? So if you were to sketch that, and again, this is not the polar curve, what we're doing is saying, how do we think of r as a function of theta? Well, the picture will look like the following. We're going to, let me grab a color here. We're going to start here at 1, and then we actually come down, and we go up, and we come back. So that this point will be at 2 pi. And then here is pi, and we should mark some additional points, pi halves and 3 pi halves. All right. So there we go. There's our curve, r, thought of as a function of theta, but not in polar, not yet, not yet. Now we say, okay, what are some interesting points? Well, we can kind of see, look, we'll mark 0 and 2 pi is interesting, and really, we see this as a periodic function of 2 pi. So if we understand what happens from 0 to 2 pi, it's going to have the same behavior in 2 pi to 4 pi, and in 4 pi to 6 pi, and so forth and so on. So we only need to graph from 0 to 2 pi. And we see, something's happening at pi halves and at 3 pi halves. So again, our scanning here from left to right translates into a rotation as we move around. So what's going to happen? Well, we sketch, and we see the following. We can mark a couple of points. We can go ahead and mark the 4 distances here, and all the points. Well, what do we see? Well, we're distance 1 at 0 and 2 pi. We're distance 0 at pi over 2. We're distance 1 again at pi, and then we're down here at distance 2, and that's at 3 pi halves. So there's our various points that we've plotted here. And now we just say, what's going on? Well, we look at the behavior, and we say, well, what's the function doing? Well, the function starts at distance 1 and gets close to the origin, and it hits the origin at pi over 2. So we start at 1, and then as we pivot, see, as we're moving from 0 to pi over 2, we're going to go into 0. Then from pi over 2, it starts going out again. And so by the time we hit to pi, we're back at distance 1. So again, this part here becomes this piece here. So there's this nice translation from that to there. From pi to 3 pi over 2, which is this part down at the bottom, we continue getting further and further away. So we're getting farther from the origin until we hit the bottom. And then from 3 pi over 2 to 2 pi, this last part here, we're going to get closer to 1 until we hit to 1. So we're coming in, then we're going out and out and out to here, and going back in again. And so that's the curve. That's the curve. Now, what do we see? Is there symmetry? It looks like it, right? Pick it up, put it down. It looks the same. So what do we have? Well, it looks like it's symmetrical with respect to the y-axis, right? Because that's the y-axis. Well, when does that happen? Well, that's true if f of pi minus theta is equal to f of theta. Well, what do we have? We have the function 1 minus sine of pi minus theta. Now, you need to know a little bit about sine. Now, sine and cosine are not pi periodic, they're 2 pi periodic. So what happens if you shift by a factor of pi? Well, what happens is you're exactly opposite. If you think about it in terms of the unit circle, see if I'm at a point, here's my theta, say is over here, then pi minus theta, pi plus theta would be exactly opposite. So if you shift by a factor of pi, the x-coordinate and y-coordinate are exactly opposite sign. So this is the same as 1 minus a minus sign of minus theta. What happened there is I took the fact that, look, I know if I shift by a factor of pi, I put a minus in front. And so I took that shift by pi out and put the minus in front. And then I say, well, wait, sine is an odd function. So this is 1 minus sine theta. Okay, and now I say, wow, very, very negative. 3 negatives all lined up in a row. Well, that becomes, lo and behold, 1 minus sine theta. And therefore, it has the symmetry. Great, perfect, just what we need. Now, before we leave this, a little story. This is true. When I was undergraduate, a long time ago, and I was in university, and our university had a newspaper that on Valentine's Day, you could print a little, what they called a love line, a little note you could print out to your significant other. And so I thought, well, I'm a math person. I like doing math. So I put in, I actually did 2. Now, I'll tell you about the other one in a very future session, way down the road. But here's one of them. And I said, look, this shape here, it's actually a very famous shape. It's called the cardioid. And so when you see these curves, what you're seeing are cardioids. Well, why? Because they look like hearts. You can see this one looks the most like a heart. And so, what was it I put? I said, R equals 1 minus sine theta u. And you're probably thinking, first off, adorable, but boy, couldn't you have just put a heart emoji? Well, this was back in the days before emojis existed. And I know that's hard to believe, but yes, this is in the pre-emoji era. So that's what I put, and I'll tell you, eventually, I married her. So it works. It works. So try it out, and if you succeed, let me know. And so R equals 1 minus sine theta u. That's right. I love you. All of my students. We love all of our students. All right. Well, let's go on and do another problem. Okay, so here we go. Sketch the curve r equals 4 sine 3 theta and identify any symmetry. Okay. Well, this should be interesting. Let's think about what's happening here. Now let's think about the sine of 3 theta. What is that doing to our period? So normally sine repeats itself every 2 pi, it just... So when you scale by a factor of 3, what happens? Is it doing a squishing it so that it repeats more often? Or is it stretching it out so it repeats less often? Which one is it? Well, it turns out it's actually going to squish it down, so it's going to repeat much more frequently. So it's going to do this kind of behavior. So in other words, instead of doing just 1 up and down, it's now going to do 3 up and downs in the same amount of time. So we can say, all right, to start, we're going to come here and say, well, let's just try to get an idea of r and theta. The 4 just is a vertical stretch. So that's not so hard to see what happens there. So, so here's 2 pi. So what we'll do is we'll split this into thirds. So we're going to have 2 pi thirds and 4 pi thirds. So it's easiest to just say divide it by a 3, and that gets you to the 1/3 mark. And okay, if you double that, that's the 2/3 mark. So, okay. So we're going to have the following. Now again, we're not yet to graphing in polar. We're just saying, well, how does... Oh, whoops. Ha! I mixed up my r and theta. That's theta. Theta is my input. R is my output. There we go. So what we want to do, did I do it right on the other page? Yeah, I did it right on the other page. Okay. Phew. I was worried for a second there. So what we want to do is say, okay, what's our basic shape? So we're going to see the following. We're going to go up, down, back up. And we're just going to keep repeating up, down, back up, down, back up. Okay, so that's what happens. Up to a height of 4, down to a height of -4. So the next thing for us to mark are where are the interesting points? Well, the interesting points are going to be at the zeros. So that's at pi thirds, halfway in between. Here, pi, halfway in between 2 pi and 4 pi thirds. And then here, it'll be 5 pi thirds. All right, but there's also interesting points. Those are the zeros. The other interesting points, and we'll try to get a different color here. Okay, we'll use this one here, is the peaks. So this is at pi over 6. Down here, halfway in between those two, which would be, well, pi over 2, right? Now, if you're not sure how to get halfway, you just add the two numbers and divide by 2. Pi over 3 plus 2 pi over 3 is pi, so that's pi over 2. And then up to here, that would be 5 pi over 6. Down to here, that would be 7 pi over 6. And over here, that would be 3 pi over 2. And then finally, when we come to here, that would be 11 pi over 6. Okay, wow. So we're going to have a lot of interesting points. So let's make some notes. Yeah, we're going to have boom, doom, 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 doom. Okay, and there we go. Wow, okay. Well, let's think about what's happening here. So what I'm going to do is I'm going to start by sketching our plane, because when we're doing polar, we're still on the plane. That hasn't really changed. And then I'm going to mark sort of some interesting angles. So anytime we come into 0, that's an interesting angle. And what I'm going to do is I'm going to put a dashed line at that angle. So where do we have that? Well, at theta equals 0. Okay, so I'm going to put a dashed line at 0. And where's our next one? Pi thirds. Pi thirds, by the way, also known as 60 degrees. So 60 degrees. So 2 pi thirds, also known as 120 degrees. And the next one, pi, okay, known as 180 degrees. I should mark theta equals 0. And, well, you can see where this is going. Okay, come down here. Where's our 4 pi thirds? And come down here. And here's our 5 pi thirds. All right. And now we're actually going to be in pretty good shape, right? So let's start with this first piece here. What happens? Well, we're going to start at 0, and then we're going to get further and further out till we get to pi over 6, and at pi over 6 we go out to a distance of 4. So this is at theta equals pi over 6, and r equals 4. So we're going to come out, and then we're going to come back in. So you're coming out, farthest point, come back in. So that as we scan here from 0 to pi over 3, and then we say, translate that into this piece, we see, aha, this up and down becomes sort of a leaf right there. Great. Now, what happens next? Well, next we say, okay, well, from pi over 3 to 2 pi over 3, where do we go? Now, oh, okay, this is good. Be interesting, right? This is going to be like, what? Okay, here we go. We're preparing for ourselves for our like, what? All right, now, what's the what going to be? It's negative, right? So normally, if I was going from pi over 3 to 2 pi over 3, I would come up and down. But because r is negative, I'm not going to be coming up here. I'm going to be coming this way. So I'm coming this way. At pi over 2, negative 4, that says, think about our direction. Okay, we'll mark it here, right? So we first would go to pi over 2 this way. That's our direction. And then we walk backwards. The negative 4, that indicates it's a backward stroll. So this point right here, this is theta equals pi over 2, and r equals negative 4. So what's going to happen is that after we come off of this leaf, we're going to come off and down and back up. So that's the second part here. Because r is negative, it goes and gets reflected. So instead of going from here to there, it ends up going from there to there. Okay. Unfortunately, my hand is not very transparent, but hopefully you can see what's happening. Now, that gets us up to here. Well, now we're at 2 pi over 3 to pi. So we want to understand that part. Well, we see, okay, we're going to come out here at this point where theta is 5 pi over 6 and r equals 4. And we see, okay, we're coming off from the origin, out, and back in again. Okay? And so now we're to the halfway point. So the next interval from pi to 4 pi over 3, which is this part, would normally be here. But r is negative. So we're not going to be down here. What will happen is we're going to be back over here a second time. So not only is this theta equals pi over 6, r equals 4, it's also theta equals 7 pi over 6, and r equals negative 4. So that's going to be the next one. We'll keep going. Now we're down to the 4 pi over 3 to 5 pi over 3, and we see, look, it's just going to behave like we think. It comes out to our far point, back in. Our far point being at, let me move this up so we can write it down here, theta equals 3 pi over 2, and r equals positive 4. And then our last part, coming back into here, will be here. So lo and behold, that's between 5 pi over 3 and 2 pi, but again, we're negative. So we're not going to be here, we are going to be back here. And so this point is again done twice. So this is also 11 pi over 6, and r equals negative 4. So that's the shape. It turns out that we're going to have what looks like it feels like we're missing these pieces, right? That there's these sort of every other part gets covered. But we're not actually missing it. What ends up happening is that things get covered twice, so that as we trace, we cover everything 2 times. And so that's our picture. Now, can we see the symmetry? And yeah, we can see symmetry. Now, one symmetry we can see, and we can just sort of pick up, put it down, and so this has symmetry with respect to the y-axis here. And you can check it out, and we'll skip the intermediate steps, but that says 4 sine 3 pi minus theta is the same as 4 sine 3 theta. But of course, there's other symmetry here. And we like to exploit symmetry because when we use symmetry, we reduce the complexity. So another symmetry that you can see is that there's like a rotational symmetry going on here, which is if you just take this picture and you rotate it by an angle of 2 pi thirds, you get the same picture back. And so that's something else that we could use if we were working on problems. And by the way, we're going to see this again in a future session, in the very near future, where we might be saying things such as, hey, let's say something about what's happening to this shape that's being traced out. And this is why you have to be careful with polar, because it looks like, oh, if I go 0 to 2 pi, I'll just cover everything exactly once. Well, because of our ability to go back and have negative r, you can actually cover things twice, even though it looks like you only did cover things once. So the moral is, be careful. Be the right amount of careful, because interesting things can happen. All right. Well, good. Well, let's try another problem. Okay. For each of the following 3 curves in polar coordinates, select the picture which corresponds to the curve. So you have r equals 2 plus cosine theta, r equals 1 plus 2 cosine theta, and r equals 1 plus cosine 2 theta. So we have the 3 curves, we have our pictures, and we're wondering, okay, which one goes with which? Now, it's possible for us to say, oh, I can describe things in a different way, and I still get the same result out. So be careful. Be careful. All right. Well, let's take a look and see what we can see. So, for example, let's start with the first one. R equals 2 plus cosine theta. And we think about it. Well, if we think about it and we say, look, I know how to graph this in terms of r as a function of theta, as we think about in our old style of plotting things, it just says take the cosine and shift up by 2. So, okay, so we take the cosine and we shift it up by 2, it would look something like this. Now, what do we notice? Well, one thing that we notice is it says, look, you never get close to 0. You always are bounded away from 0. So what's going to happen is that as you move around, you never hit the origin. So as we look at the pictures, we say, hey, there's only one of these that never hits the origin. It's this bottom one here, right? And you can see what happens. Well, we're far away at the beginning, and then we move closer at about the halfway through, and then we move back farther away. Well, that's the behavior. Far away, move closer about halfway, then move back farther away again. So we say, aha, this number 3, that corresponds with A. All right, well, that one's not so bad. Okay, well, let's see. Let's try another one. Well, let's try B. What could that do? So 1 plus 2 cosine theta. Now, what's going to happen is because of that factor of 2, we will go negative for a part, but you can actually plot things. So, for instance, at theta equals 0, we're at 3, and then what will happen is it will go down, but the worst it will ever get is -1, and then it'll come back up to 3 again by the time we hit 2 pi. Okay, so this is theta, this is r. So how do we think about this? Well, it says you're far out, you come close, then you sort of cross over, and then you go back up again. And in particular, if you think about intuitively what should be true, is we're going to hit the origin. Okay, so but both pictures hit the origin. But now we could say, well, what should be the case? I should have it be the case that if we think about what's happening on this axis here, I should see something that's a distance out. Now, we don't have the distances marked, so we don't know these relative distances. But you see here how at pi we have a negative number? That says when I'm looking in this direction, I've walked backwards. So I should see 2 points on that mark. Now notice here, you only see 1 point. So I should see 2 points. One from theta is 0, positive mark out. One from theta equals pi, and a negative value for r. So that tells us that this part right here, this is b. But if we look at the picture, now we can start to understand. It's like, okay, we're going to start out far away, move into the origin by some angle. So we have this angle right here and this angle right here. Those angles, I'll call it alpha and beta, correspond to these parts right here, alpha and beta. See, it's where we cross over, and on the other side, we have this little thing around. That's the part down here. And then we come back and go out from 0 and head to value 3. So it does match. It matches the behavior. Now, if we were not being cautious, we would say, okay, the last one has to be that choice right there. But we're cautious. So let's see if we can reason our way through it. Well, what is this one going to do? We see there's this factor of 2. See, there's been a 2 everywhere. It's just a matter of where does the 2 go and what effect does it have. Now in this case, what's going to happen is we see, look, the 1 plus cosine, it's never negative. And what will happen is it'll move up, but instead of doing 1 cycle through, it's going to do 2 cycles through. And so, well, where do we hit? Where are our interesting points? We're going to bottom out wherever we would have cosine be -1. Well, cosine would be -1. Normally when we plug pi in, because of the fact we have 2 theta, it would be at pi over 2 and 3 pi over 2. So what this tells us is we say, look, here's this pi over 2, here's 3 pi over 2. All right, and what should be the case is that we're going to start out, come in, and then we're going to go back out. And then we're going to be far away, come in, then go back out, then come back in, then go back out. So out, in, out, in, out, in. So that does match our behavior. So it really is, truly, that is C. All right, and we can see small changes in where we put that 2 can lead to very different behavior. I mean, the original shapes are quite distinct from one another. And we would say, wow, they're very different curves. But then when we look at this, say, they don't seem that different at all. So it's polar curves are a little different. You got to get used to it with practice, And it doesn't hurt to have a computer say, well, I'm not sure. Let me have the computer plot it. That's not a bad way to build intuition. All right, well, let's try some other problems. We should do something about tangent lines, right? Because that was our other topic. Find the tangent line for r equals 1 minus cosine theta, and theta equals pi over 2, and theta equals pi over 3. Now we sketched this curve before. This was our cardioid. So I'm going to just get a quick sketch of it again. I'm not going to rederive it. You can go back and take a look at what we did before. But if you remember what this looked like, it had the following behavior, where we start off here, and then we would go out and move up, head over to there, and mirror thing happening on the other side. So that's roughly what the curve looked like. And now we're saying, well, what are we after? We're after the tangent lines at specific points. So we want to do it at pi over 2 and at pi over 3. Now pi over 2, that's easy to mark. So we want to find that tangent line. And pi over 3, that's like a 60-degree angle. So it's not quite clear where it is. Maybe somewhere roughly here. Looks dangerous. Well, let's see where we go, and then we'll know. So how do we go about finding our tangent lines? Well, what we need to do is find ourselves points and slopes. So let's start with pi over 2. We'll start there. At theta equals pi over 2, we can plug in for r. R equals 1 minus cosine of pi over 2. So that really says r equals 1. Cosine of pi over 2 is 0. So now we know our point. In fact, even if we didn't know how to convert, we would be great, because look, that says go up a distance of 1. So this really corresponds to the point 0, 1. Okay, now how do we do our slope? Well, the way we do it is we say we're going to start here in polar coordinates, and then we're going to transform it to parametric, because we know how to find slopes in parametric. So the way we do it is we're going to say let x, we're going to let that be r, so that's 1 minus cosine theta times cosine theta. And we're going to let y be r, 1 minus cosine theta sine theta. And now we say, okay, look at y prime over x prime. And this is the part where I often make a mistake. And so I'm pausing here just so that I hopefully remind myself not to make this mistake. The y prime is this one. The x prime is that one. And so it's easy to forget, oh, yeah, right. You have to sort of do things in the opposite way. So here we go. Take the derivative of the first. Derivative of 1 minus cosine theta is sine theta times the second, sine theta, plus the first, 1 minus cosine theta times the derivative of the second, which is cosine theta, all over, okay, here, derivative of the first, sine theta times the second, cosine theta, plus the first, which is 1 minus cosine theta times the derivative of the second, which is negative sine theta. Okay, so there we go. That's our y prime over x prime. And we could try to clean this up if we wanted to. We don't necessarily have to. And we just need to plug in our value for theta. So we plug in our value for theta, and we see what happens, and then life is good. So at theta equals pi over 2, well, what happens? We get y prime over x prime. Sine of pi over 2 is 1. So we're going to get 1 times 1. Okay, that's 1. And then cosine of pi over 2 is 0. So 1 minus 0 times 0. So that's going to be, well, plus 0, right? Because 1 times 0. Downstairs, sine of pi over 2 is 1. Cosine pi over 2 is 0. So 0. And then here we're going to have 1 minus 0, which is 1, then times negative 1. So that's minus 1. So we get negative 1. So now we're like, great. That's a wonderful slope. So turns out here our slope is negative 1. And now we're happy. We have our point. And not only is it our point, look at what kind of point we have. It's the y-intercept. So we can say our y equals m, which is minus 1, times x plus b. So y equals minus x plus 1. That's the tangent line there. All right. Well, that's great. Beautiful answer. Now, let's see what happens at pi over 3. Okay, so to help us at pi over 3, we might want to remind ourselves some trig values. So sine of pi over 3 is root 3 over 2. And cosine of pi over 3 is a half. Now, these are just standard values for trig functions. If you're struggling with remembering them, the thing that really helped me was teaching trigonometry for 2 years. After I did that, I always remembered my basic trig functions. But, for these, you can look them up. There's lots of ways to remember these, but we'll get to that some other day. So for now, let's suppose we have these. Okay, so we have these. All right, now we're just going to be patient and work our way through. So at theta equals pi over 3, we get y prime over x prime. Well, root 3 over 2 times root 3 over 2 is 3 over 2. 1 minus a half. Oops, 3 over 4. I'm sorry about that, right? Root 3 over 2 times root 3 over 2, 3 over 4. 1 minus a half is a half times a half. So that'll be 1 over 4. Okay, great. Nice answer upstairs. Downstairs, root 3 over 2 times 1 over 2 is root 3 over 4. And then we're going to have 1 minus a half. Okay, that's a half. And then times a minus root 3 over 2. So that's a minus root 3 over 4. So we end up with 1 over 0. Well, what? Wait, what does that mean? Okay, what does 1 over 0 mean? And it does not mean more work. What does it mean? Well, it means that at that point, the y-coordinate is still having a change. So we're still moving up and down, but the x-coordinate, it's not changing. It's stuck in place. So it means we're purely up and down motion. So this means a vertical tangent. So that's what we have. It's a vertical tangent. So that's great. Now, so we're almost done with our other one, although what else do we need? We do need a point. So to finish off our other place, we say, look, at theta equals pi over 3, well, plug in cosine pi over 3 is a half. So we would have r is equal to 1 half. 1 minus a half. And what do we get? Well, our x value would be r, 1 half, cosine theta, and our y value would be 1 half sine theta. Well, we know these values, so we end up with 1/4, comma, root 3/4. All right. And finally, we say, but look, it's a vertical tangent line, which means it's the x equals something, because that's what a vertical tangent line looks like. It's just x equals something. There's no y change. So we read off our x value, and therefore our answer is x equals 1/4, straight up and down. All right, and there we go. Those are our tangent lines. Great, beautiful, beautiful. All right, well, I think we can try one more. Let's see. All right, here we go. Find the angles between 0 and 2 pi for which the line tangent to the polar spiral, r equals e to the minus theta, is horizontal. And that is, the slope of the tangent line is 0. Well, first off, what is this? Now we know what e to the minus theta does. If we have here theta and r, it says, look, e to the minus theta starts at 1, and then it just goes down. Now, how does that translate? into the curve in terms of the polar, well, the translation which says what? What you have is you're going to start at 1 when theta equals 0, and as you go around here, which is the same as reading from left to right, so as we go this way, we're going to get closer and closer. So we just keep getting closer and closer. So it's going to do something like that. So what are we after? Well, we're after the angles. So there's some angles here where, maybe like this angle here, I don't know, where when we look at this tangent line, it's flat. And I don't know what the other angle is. Who knows? It's flat. Well, it's not clear what the angles are, but that's what we're after. What are those angles which make things flat? Well, if we think back to what we have, the way we find tangent lines to polar curves is we make things parametric. So we have our x of theta would be our r cosine theta, and our y of theta would be our r sine theta. So if we want a flat tangent line, which is what we're after, flat tangent line, really that tells us we need y prime of theta to be 0. Okay, so what is y prime of theta? Y prime of theta, well, here we go. It's going to be the derivative of the first minus e to the minus theta times the second sine theta plus the first e to the minus theta times the root of the second, which is cosine of theta. All right, and we're going to set that equal to 0. Well, you can pull out the e to the minus thetas, and then you have minus sine plus cosine. Now, e to the minus theta, it's never 0. So if the whole thing equals 0, that says this part is the part that has to equal 0. So, oh, perfect. Well, that gives us sine of theta has to equal cosine of theta. Or if you divide by cosine, we can say, hey, that's the same as saying tangent of theta is equal to 1. Wow. Tangent of theta equals 1. We know that. Think about taking the arctangent of both sides. So theta would be arctangent of 1. Well, that gives us pi over 4. But then we say, whoa, hold on. Arctangent only covers half. And so where's the other half? The other half, see, arctangent only goes from negative pi over 2 to pi over 2. So the other half over here. So the way you get that is you add pi. So, or pi over 4 plus pi, which gives us 5 pi over 4. And therefore, our answer for what values of theta, we have pi fourths and 5 pi fourths. So, well, that's it. That's the answer. Our picture now probably is not very accurate, right? Because it doesn't look like an angle of pi over 4. Well, it's hard to get the picture right. But qualitatively, the picture is right. And so we have the right ideas. Okay, well, that's a nice cool down problem. Keep at it. Keep doing the problems. The more you do, the better you're going to get. And so keep going. I believe in you. And I hope to see you again in another session.